Hi all my integration friends. In this video, I'll demonstrate the concept and how you can take a dataset, even a dataset that you have or using an open source, or maybe setting up your own dataset, labeling that. Taking that dataset and train an AI model and to get that working in an Axis camera. So those who wants to try it, they can follow this, and I have some guides that you can use. But for those who do not intend, it may be still interesting on understanding the process of doing this thing. So this is very much related to a video, a podcast, Innovation in Progress, that my friend and colleague Kwang, we had discussions around this topic. So in this video, I'll go a little bit deeper and demonstrating how you do this. So I'll put the link to, if you want to see this podcast, I'll put a link in the description below. So what are we going to be doing? Well, let's pick a data set, and I will use a open source data set that most people would, recognize. So this is very much related to an ACAP that I did called hand gestures that I used Hagrid dataset. In this case, I will use a similar thing, but it's the game of rock, scissors, and paper. And you can probably do some really cool stuff. You can probably make a game that you play against a camera, or you can have the camera being the judge, or anything. But the idea here is not getting this to work or making an application of it. It's just about understanding how to train a data set. So I found this data set on Universe RoboFlow. I'll put the link below. It's a great place if you want to find some open source data sets to train your models on. And there are a bunch of images. So this is a group of people that's been taking images of different hand gestures and labeling them. And what we're going to be doing is using the data set. And in this case, it's so they have different versions of the data set. You can also you see here, there are models. And since we need to train on YOLO 5, these, depending on how you're going to be training your data set, the images needs to be structured and labeled in a specific way. And in this case, it's very good that there is a YOLO 5 where you can just click that one and download. I've already done this. I'll show you soon. And the structure of this zip file that you're about to download. So that is a data set that we're going to be using. And to train, we will use Ultralytics YOLO 5. That is their easiest way and the documented way how to train a model and how to export and model. And the camera is a little, has to be very specific, that I'll go through in this video tutorial. And now when we have the model, we need to get it into an ACAP, which can be very challenging if you are not a C developer or an ACAP developer. So I developed an open source project called DetectX. And the whole idea here is this is a complete ACAP that runs a model where you're having a user interface to do some filtering and having some outputs like events, but you can also get the bounding boxes over MQTT. I'll demonstrate that, the whole application at the end when we get everything working. So those are the 4 things that we're going to be using, and I'll put the links to all of these in the comments below. So let's start with the setup that I have. So what you're seeing here now, I have my access to my AI server, which is just a secondhand gaming PC that I bought, installed Linux, just to get the GPU, which is a RTX 4070 Ti, which I think 12 gigabyte of memory. And this is Linux that I have on my server. So what it's a headless server, so there's no monitor to this one, so I'll just use this for running models. So what do you need to get this working? Well, you need to have Python installed, and you need to have Git installed, and you need to have, or preferably, a GPU. You do not need a GPU to do this training, but it will speed things up very, very much. Now, and I've created a directory called YOLO to ACAP. That's where we're going to be doing this project. And I've downloaded the dataset, so we can look inside here, and we see that, yes, I have a directory called rock, paper, scissor. That's where my dataset is that I extracted from the zip file. If we go into this directory, and we can look what's inside there, we can see there is a file called data.yaml, and there's some README from the developers of the dataset. There are 3 directories containing images and labeled text files. So one of them is training. So these are images going to be used during training. And then there is a directory called valid. So this is a group of images that's going to be helping with the reinforced learning during training. That after, during training, it will predict something and saying, I think this is a scissor, and then inside the valid is also the labels file, which is the truth, and say, no, it was a scissor, and then the training will adjust the parameters. So we can go into the train directory, and from in here you see 2 directories. So we can just look inside there, and what you see is a whole bunch of JPEG images. And we can also look under labels. You see text files having the same file name as the JPEG image, and inside this text file tells what was detecting in this image. So somebody has been labeling this manually and saying, in this bounding box, it was a hand as a scissor, or a rock, or whatever. So labeling is probably one of the most tedious work to do. It's this is nice to work with an open source dataset, which everything is pre-labeled. But if you're building your own, you have to do the labeling. Clear. Okay, so now we will install YOLO and everything needed to do the training. I will recommend that if you are working, so everything here is now Python scripting, that if you are having a bunch of different Python projects, all these packages with versions may, collide or do something, and then you can use something and install something called Conda, which I have, and I've created an environment with Python 3. So Conda activate, and I have an environment that I just call YOLO to ACAP. So you see now here that I am inside this environment, separating all the packages that's going to be installing during this process, and it's not going to impact any other Python projects that I have on the same machine. So now we are going to clone the directory. And so the command is git and clone, and this is the URL to the Ultralytics YOLO 5, and we can just press enter, and there we have everything. We can go into, as you see, I have now another directory called YOLO 5. We go into the YOLO 5 ls, we can just see what's in here. So there are a bunch of files and directories. There is this one, train Python. That's what we're going to be using when we're going to do training. And there are models. So these are configuration file in how to do your training. And as you see here, there are a bunch of YOLO 5N, which stands for nano, meaning that you want a data or a model with approximately 1.7 million parameters or weights. People will typically use weights. So the model is just a bunch of parameters and weights. So if you're training with N, it's going to be a nano, 1.7 parameters, 1.7 million parameters. If you're using this S, small, it's going to give you a model of approximately 7 million parameters. If you're going through the medium, it's going to be 20 million. I've successfully run medium models, and I have not tested and looking at the YOLO 5 large and the extra large, which is most likely it's not going to fit in the camera. It doesn't have that kind of resources. Start with the YOLO 5S and not see if you're not happy with the quality. After validation, you can move up there. But it also depends on the use case. If you are just going to be using object detection, something there, something's not. You need a high quality. But if you're going to be doing tracking, you need the inference time when it analyzes each frame as quickly as possible. You need those boxes in each frame as close to each other as possible, giving you a good tracking that ID. But if you have like 300 milliseconds between them, so you're going to get like in one frame, it's going to be one box here, and then it's going to be a box there. So the post-processing and trying to say that this was the same object is going to be really hard, or was this a new object that just came in there? So depending on if you're going to be doing tracking or just detecting. If you take a parking space transition, if a parking space is occupied or free, that inference could take a minute. That application would still work because it's a very, very slow changing scene. So going back into, so we're on the YOLO 5. So there are things that we need to do in order for the cameras to accept the model. First, how to train it, and then how to export it. So in the access documentation, there is that we need to check out a very specific branch of this repository. Something happened. I have no idea. I'm not the expert in trading. I'm just the one looking into what recipes actually works. So since this is working, I'm fine with that. So now we just switched into a different branch, and then there is also a patch that Access provides in their documentation, which is fetching with curl and getting this. So this is what file storage Amazon YOLO patch A9. So in the documentation it says A8 for ArcPic 8. What I noticed is that if I do this training and I'm going to be running it on the upcoming ArcPic 9, that model is not going to be accepted. And if I use the A9, I get a better performance. My observation is around 10-15% of using the A9 patch instead of the A8. So this is in my documentation and in using that. So git apply. So now we applied the patch. So what it did was we can just do cat model and YOLO I think 5v5, sorry, S. So let's just look at so what it did was, so these are a bunch of configuration parameters in this file, and this patch adjusted a couple of these values in all these models in order for the cameras to accept it. So the next step is that we need to install all the packages inside so there's a file called requirements text, just listing a bunch of packages that we need in order to do the training. And yeah, So in this case, yes, I do have everything. So we are ready to do the training. So let's just clear this. So let's start the training. And this is the line that we are going to be, I'll go over this from start. So it's all command line. So Python, meaning that this is a Python script, and the Python script that we want to be running is called train.py. I'll give a name to the model, so which is a good or recommended way if you're training different models to separate them. And I decided in this case to have a fairly high input resolution. So the models are always aspect ratio 1:1, and they all expect different image resolutions inputs. And I'll be going for a 960 times 960. And there are some reasons why I chose 960, because there is a 4:3 aspect ratio inside the camera with a 960 height. So what is going to be happening that the ACAP will use a 4:3 and not 16:9. So it's not going to be detecting on the edge. So different ways to solve this with models that are not where you can run 16:9 image resolutions inputs. You can do letterboxing, meaning that you will only you'll do like the old VHS where you're having black borders on top or bottom. You can do cropping 1:1 inside the images. What I will typically do is I use a 4:3 and squeezing that into a 1:1. So the 4:3 is going to become a 1:1, meaning it's going to be affected a little bit. I'm okay with that, depending on the use case. So this, to me, has been shown to work very good. I haven't seen any big negative impacts, not on the use case that I've been working on. The next parameter are batch size, and that means how many images is the model going to be training simultaneously with one batch. So if you took one image in a batch, you will just take one image at a time, and it's going to take a long time. You have two images, it can process two images at the same time, or in this case up to 30. So how many images that can be used depends on how much memory you have in your graphics card. I've tested, and I see in this case 30 is good for me. I'm keeping it under 12 gigabytes, so I'm not exhausting the GPU memory. But this is something that you need to do trial and test. And then we'll come into epochs. That basically tells the training how many times should the training see the complete data set. So we'll go through the whole data set and adjust all the parameters. That's epoch 0, or the first epoch. Then we'll do the same thing again and just keep, iterating over and over. So the more epochs that you have, the better quality you're going to get. I typically recommend it would be like going up to 300 epochs on the training. But for this demo, I'm just going to be using 50. And if you monitor the training, you can see that the learning curve is flattening out after a while. So it doesn't really give you any additional value to do more epochs. So this is just something that you need to learn on trial and error to see what works for you. And then we're going to be telling it where the data is. So it's in that directory, rock, paper, scissors, and that's the data YAM. So it's going to be opening that one and understanding where the images are located and the labels and how many labels there are. And then telling it which configuration. So in this case, I'm telling it to use the YOLO 5 version with a small. So I'm training it with 7 million parameters. And let's just hit enter. So now everything started. It just, looks up everything and plotting labels. So it's just so now we actually started. So what you see here at the bottom is the epoch, and it's on epoch 0 out of 49. So here I can actually monitor how much GPU memory am I utilizing, and I'm exactly 12 gigabytes, which is how much memory my graphics card has. So these are a bunch of values that those who works with model understands very well. So by these values, you can see how the training is progressing. And then it just goes over the images. And then we can see here on the epoch 1, how much is left. So we're up to, let's see. And then you can see the time here, and you can most likely make a time estimation on how long is this going to take. The biggest I've had was, I think, with Hagrid, and that took about a day and a half to do the training on the number of epochs and everything I do. So I can show you while this one is going on that, let's see, I'll start a new. So we see how the training, and I'm just connecting with another putty. And so now we can go into the YOLO 5. And so nothing really changed. So the ones that the subdirectory is called runs. So that is where the model is going to be stored. So let's go into runs, and I know there's always going to be a subdirectory. Once it started in training, it's going to be called train. And looking in here, we have the name RSP that we gave the model, which stands for rock, scissors, paper. I wanted to have a short name. So this is currently ongoing, so we can go into rock, scissors, paper and look what is going on here. So you can open up it generates JPEG images out of all the training images and showing the labels. So during training, you can open up these images and just seeing that the images seem to be correct, and the labels, the bounding boxes. So it's actually showing bounding boxes in the images. If everything looks correct. And then there is this one, result CSV. So you can open up this CSV, and what I typically do on a long training, I would open up the CSV. I will send that to some LLM. I usually use Claude, and just asking how is the training progressing in this thing, because I'm not good enough to understand exactly how these values in this. So it's just a bunch of tables with values and epochs and everything. And then I could ask it, how many more epochs do you believe is needed before the training flatten out? And it makes a prediction how many epochs it should use. Then there is a subdirectory called weights, and we can go in there. And this is the ongoing training. So this is the PyTorch file. So the best and the last. So once the training is complete, that's the one we're going to be exporting to TF Lite. And a cool thing here that, okay, what happens if you're going to be doing a long run on training and something happens, something crashes or whatever. So I'll just wait for that epoch 3, and let's just do Control C. So I just interrupted the training. In Python, you can do train. You can use this Python train and resume. I was a little hiccup there. Python, resume. And now it's just going to be initializing again, and it should be starting off at epoch, was it 4? Yeah, so it just continues. And if you do multiple trainings, if you go back here, so you need to keep track when you're exporting. So during in the directory YOLO5 runs, and currently it's just going to be, I have just trained this one once. So if I'm not, after I'm trained and exported and I'm not happy with it and I want to retrain it with different configuration, it's going to generate a RSP 0 and 1 and 2 and 3 and 4. So it always maintain all your previous trainings, not to lose them. And this is important when you have multiple, if you train it multiple times, and you're exporting it, you need to make sure that you're getting the right index. But we'll just leave this. YOLO. Oh, we don't need that one. So we are now. I will just pause and get back when the training is done. So we are back in, the training is complete. So we can now start looking at the table. So let's start with just doing a clear. And now we're going to be exporting it. So we'll be using this command and taking it from start. So it's going to be Python script, and the Python script is export py. And the weights we're going to be exporting is the PyTorch file that's under runs, train, RSP, weights, best PT. And we're telling it to do a TF flight and with an integer. So what does this mean? Well, the PyTorch is running floating point to get the precision. The camera is not able to run models with floating point. It needs to run TF flight quantized. And we're quantizing it to an integer 8. And what that means is, since we're not moving to whole numbers and not using floating points, we may lose some precisions. And how much quality am I losing? It's really hard to say because it depends on the model and a lot of things. People that are used to be running their models on PyTorch may be concerned over running that in quantized TF flight. And yes, you're going to be losing some, but there are some compensation you could do. So if you have the situation that you're running a server with a GPU and running your PyTorch file, but in order to serve a huge number of cameras or a number of cameras, you may need to reduce the input resolution size in order to be able to serve them all. In this case, the camera is running self-sufficiently, so what you could do is, so one compensating thing you could do is increase the input resolution, going from example 640 by 640 to 960 or even 1440, or so that could be a compensation, but it's quantized into whole numbers. The ArtPic 8 can only, there are two ways to process them or the models is per tensors or per channel. The ArtPic 8 only supports per tensor. If you do per channel, it's gonna run, but you're not gonna get any data out of it. The upcoming ArtPic 9 can support both per tensor and per channel. The documentation recommends using per channel, but training it with per tensor means that this model in the ACAP, or it can be used in both for ArtPic 8 and ArtPic 9. And I'm also telling it to use an image size of 960. So we export this, and this is going to take some time, and I'm going to be pausing and coming back when the export is complete. So now we have exported TF Lite, and it's located in where it shows here, runs train RSP TF Lite. So let's do clear. So for building the ACAP, we're going to be cloning the DetectX repository. Let's not do that in the YOLO 5 directory, so we can go here and just check here. Well, I see the dataset, the YOLO created dataset directory there. So to clone, we use this git clone, and this is the URL to my DetectX repository, and clone that. And there we go. So we see that the I have now the DetectX. So let's go to DetectX and let's clear this and look at the directory. So it's already been pre-compiled with the Coco SSD, which is the common objects that many training and examples are using. So we will overwrite that. We can actually just remove that one right now. It's so there is a directory called app, which includes all the source code, and inside there there is a directory called model. And if we look inside there, we see the labels text for the Coco, and we see the model TF Lite, and there is a model JSON that describes to the ACAP exactly how this model, the inputs and outputs, works. So we are going to be replacing this this model, which is the Coco model, and we can copy that one from my home directory, YOLO to ACAP, and it's going to be under the YOLO directory, runs train RSP weights and best. So it's going to be best PT and a best TF Lite. So let's copy to this directory and to the file model TF Lite. So if you saw here, this file was 2 megabytes large, and if we look now, it's the model we trained, which was 7 million parameters. So now we replaced the model TF Lite, and now we're going to be replacing, if we look at the LS labels. So, oh, sorry, cat. Just show the content. So here are all the labels for the Coco datasets, and we're going to replace that. Let's do clear. Copying the from the dataset. Now let's do this cat. Just show the input from the let's see, YOLO to ACAP, and the data set is right there, and the data yum. So these are the 3 labels, so I'm just marking these and copying that one, and now I can nano the labels file and control KK. Let's just remove all of these and paste in those 3 labels. So it's going to be paper, needs to be 1 label on each row. Control S, save, and there. So now we replaced that. The only thing that we need to do now is let's do cat models JSON that tells the runtime ACAP. So this one needs to be updated. And the way to do that is going down here to detect X. There is, let's do clear. And it's a Python script, and it's called prepare Python. So what this script is going to be doing is going to go into the T-flight model and analyze how the inputs and outputs and everything, the quantization and everything, and updating the model JSON file. So now it just runs, and I have to tell it I'm going to be doing here for a RPIC 8. The resolution I selected was 960, and it just updated the model JSON with this. So this is the model input width, model input height, so that 960 by 960. This is the quantization, so this is the value that is being used to convert whole number integers into floating point, because we need to do that. The 0 point of the quantization is 0, and the number of boxes, so YOLO 5 will typically, the output is going to be, in this case, 56,700 boxes. And every box needs to be analyzed and seeing if there was detections there. Number of classes was 3. Objectness, which is a confidence level, set that to 25 to eliminate all common, misdetections. And then setting the non-maximum suppression. So these are all overlapping boxes. It's technical stuff for cleaning up over multiple unnecessary detections, the model path, the scale mode. And this is the video width. So it's going to be capturing an image from the camera at 1280 by 960. And here we're coming into so this is a 4:3 aspect ratio. So what's going to be happening is going to take a 4:3, squeeze it into a 1:1, 960 times 960, meaning that people are going to get thinner, which is, and if you look at me, that it's a little overweight. It's not a big problem, but could be for models. I have not noticed that much of a challenge with it, but you may do. Alternative ways to get a 16 by 9 to 1.1 is either cropping, 1-to-1 pixel ratio, or you do letterboxing, squeezing in a 16 by 9 into a 1:1, having black borders on top or bottom to do that. You're losing resolutions doing that way. So in this case, it's not going to be detecting the outer edges on the 16:9, but most important stuff always happens in the middle. And that's it. So let's just build this one now. And we can do, so there's the script to build. So the first time you're going to build this is going to pull down a container that Access provides, that has the whole build chain. So just if we, looking into here, so it created this one, but we want to change name. And doing so is going, there is a file that we're going to be editing called under app, and it's called manifest. And we can change the nice name. And for this demo, let's just call it Rock, Scissor, Paper Game. And let's change the version number to 00. We leave the app name, detect X assets. Control S, saving that one. And let's do build again. Just clear, and let's do ls-l. So now we have that EAP that I installed in the camera. I can remove this one. There we go. So now into the camera. So now we are in my camera, and I have a bunch of ACAPs, but here is the installed version EAP that we got, and we can start this. The first time that you start with an ACAP with custom model, it may take a very long time before the model gets loaded into the camera's memory. It can take 10, 15, depending on the size of the model, up to almost a minute for the camera. So the ACAP will not be even though it's running, it's all occupied by initializing the model into the DLPU inside the model. So, but let's go open here now. So you should be seeing the detect X having the rock scissor game. And so this page here is for the validation. So let's see if we can get something detection. Yes, it did detect rock. Let's do scissors. Yes, it detects scissors, and we can move it around. And paper. It seems like the paper is not really, you see the confidence level? And this tells me we need some more training on this one. So the epochs, the 50 epochs was not sufficient. And possibly a larger model. It seems to detect, oh, that's a scissor box. So in this here, you can do some basic filtering. You can set the area of interest. And so if I do here now, it's going to be, detecting, oh, sorry about that, over here. But maybe in this case, for this scene, I only want to be detecting here. And setting area of interest, and we can increase the, so if I put 70 here, I probably won't be able to get the paper. Scissor 83, rock, yes. Has some challenges with paper. So meaning I need to go down in confidence level to get, yeah. So it's just, this is just due to training. If you set up the MQTT client, which I have, in this case to my local MQTT, I will get the bounding boxes published on MQTT with the pre-topic detectx. So if you are consuming this type of data into an through like a scripting like Node-RED or anything else that wants to get this data on MQTT, so it's possible. And then there's some advanced. So what you see here now is, let's do a hand, and it detects rock. So this is an event that's the ACAP just fired. And if you have something inside the camera that, reacts to the event rock or on the event stream into VMS or whatever, and you want to get a more stable event, if you have too many, so what you could say here that it needs to be stable at least 900 milliseconds before the state goes high, and the state is going to be active for 5 seconds. And I may say, okay, I'm not interested in paper and I'm not interested in scissors, so I'm not going to be detecting that anymore. Coming back to the detections, and if I put up my rock, it's going to be detecting, but let's see. So that was 9 milliseconds. Let's do 2 seconds just to show you the. So I'm connecting the rock so I can visually see it, but it takes 2 seconds before they actually event. And then the event is going to be high for 5 seconds. And when that disappears, there, the event went down. And then you have the about. So this is the model, this is the device. So the device I'm running on is a Q3536 with this firmware, serial number, CPU load, and the network load currently. But what is important here is that this is the inference time. So you can, this inference time is not only inference time, it's both the pre-processing of the image, doing the inference, and the post-processing of the results from the model. So currently this is doing 5 frames per second at 200 milliseconds, which is good. Not good enough for tracking, but for detection. And thank you. I hope you enjoyed this, and I hope it was enlightening, that you learned the concept, demystifying a little bit on how to train AI models. And if you're using this and build something cool, I'd love to hear it. I'm always open to feedback, positive and negative. And you can find my contact information in my channels, or leave a comment in this video below. And I hope to see you very soon. Goodbye.